Our game is called Death Ray.
Oh, interesting. Yeah.
And our content, we are going to talk about the reading physics first, and the gameplay method, game creation, and Kahoot.
Okay.
I'm Idru. I'm introducing the electronic magnetic wave art.
Good.
And as light wave are a type of electromagnetic wave, they follow the fundamental principles governing its propagation. And these optical phenomena like refraction, polarization by reflection, and photointernal reflection are closely related to the behavior and characteristic of electromagnetic waves. And for example, the geometric shape, the curvature, and the optical properties of lenses directly influence the behavior of electromagnetic waves. The next one. Okay. So the first one, reflection, is the result of the electromagnetic waves bouncing back at the interface. When the light strikes a surface, it may be reflected. And the refraction is a fundamental property of electromagnetic waves as they propagate through different media. When light passes through an interface between two different media, and it may change its direction. So the curvature and the shape of the lenses influence the way light is reflected. And the third one, polarization by reflection. The surface characteristic of the lens can impact the polarization state of refracting lights. And the final one, total internal reflection, when light travels from an optically denser medium to a less dense one. A phenomenon of total internal reflection is influenced by the shape and curvature of the lens and affecting how light propagates within the lenses.
When does the refraction becomes refraction? Can you go back?
Explain.
No, I'm
reflection.
asking you. Can you go back one slide, please? When does this left two?
This one,
When does it change to this?
when the light travels from different media.
Yeah. So the refraction is you go back, right? The light go back, right?
Yes.
Refraction is go different way, right? So when does it becomes? What's the difference?
So
Okay. Please add the answer to the report, please.
okay. So in our game, players can change the direction of light passage by altering lenses. There are these four lenses in the game. And the first one, concave mirror, uses the reflection principle. It reflects light rays and scatters parallel rays of light. And the convex mirror also reflects the light rays, but it provides a wider field of view. And the third one, convex can converge the light rays to a single point, and reflect towards the lens central axis. So the next one is refraction. It's concave lens and it's using refraction. So it's also, it can scatter parallel rays of light, but also causes light rays to refract towards the lens of central axis in the front. So the relevance of lenses to electromagnetic waves lies in their important roles as components for controlling and guiding it within optical system. And these optical components play various roles in different applications.
Okay, so my name is Cody and I'll be introducing images. So there are two types of images. One is real and one is virtual. And the difference between them is that real image can be formed on the surface. So for instance, the image created by the projector can be formed on the screen. And on the other hand, virtual images are formed by the backwards extinction of the light rays. And so a kind mirror is an example of a virtual image. And so first I'll explain the spherical mirror. And so the formula to find the image distance formed by a spherical mirror is given by 1 over the object distance plus 1 over the focal length equals 1 over the image distance. And f, the focal length of the spherical mirror, is given by negative r over 2. And r is the radius of the curve. And so for a plane mirror, the r approaches infinity. So that makes the object distance equal to the image distance. And for the spherical mirror, real image formed on the same side as the object, and virtual images formed on the opposite sides. Okay. So on the right, we have the convex mirror, which only forms virtual images, no matter the distance from the mirror. And it's also called a diverging lens because the ray diverges, and it's called a convex mirror because the curve is going outwards. And next we have the concave mirror or the converging mirror. And so for converging mirror, when the object is beyond the focal length, a real image is formed. And when it's within the focal length, virtual images are formed. So now we have the thin lens, and they use the same formula as the spherical mirror. And however, the focal length in this case is given by 1 over p, and p is the surface power. And the surface power relates to the index of refraction of the lens and its surroundings, and also the radii of both curves. So for the R1 curve of a convex lens is positive, and R2, the radius R2 is negative for a convex lens. And also, for thin lens, the real image forms on the opposite side of the lens, and the virtual image forms on the same side of the lens, and which is exactly opposite of the spherical mirror. Okay. So the concave lens is similar to the diverging mirror or the convex mirror, and it only forms a virtual image no matter the distance from the focal length. And as for the convex, As for the convex lens, all all converging lens in, so I typed wrong. For the diverging lens, it has the same characteristics of the concave mirror. So when the object is beyond the focal length, a real image is formed. And when it's within the focal length, a virtual image is formed. Yeah. And now I'll give a quick summary on the images formed by different lenses and different mirrors. So for a diverging lens and diverging mirror, the image is always upright and virtual. And the diverging lens is called concave because its curve is inward, and convex is because the mirror's curve is outward. And for the converging lens and converging mirror, both of them, when the object is within the focal length, it's always virtual. When it's directly on the focal point, there is no image formed. And when it's beyond that, the image is real. And similarly, converging lens is called convex because the curve is outwards, and concave mirror, the curve is inward. And here's a small thing that you might have noticed is that real images are always inverted, and virtual images are always upright.
So Cody, why are you explaining all these?
Because the physics we use in the game relates.
Can you show the game first? Because I don't see the context.
Okay. Sure. I'll show you. So here's our gameplay menu.
Okay.
And so the main goal of the game is to move the death race and try to hit Albert Einstein.
You're trying to kill him?
So, and the challenge is that there is a 10-second timer, and the Albert Einstein's position is randomized. And there are different lenses and mirrors like we previously mentioned.
That's why. So there are lenses you explain is going to be the game.
Yeah.
Oh, I see. Okay. And that makes sense.
Yeah, so there are 4 different lenses, and as you can see, when the light goes through them, they have different refractions and.
Oh, okay. Now your presentation makes more sense.
Yeah.
That's
and
good.
So the controls is very simple. So WASD to move the rays, and a space, or you can click the top button to switch between the lenses and mirrors.
Oh, you can change the lens to mirror?
Yeah. So there's
Okay.
lenses and mirrors.
Okay.
And there's a small restriction is that switching and moving only works when the death ray before the death ray reaches the lens and mirror, because when it goes through the lens, it's quite difficult to reset. And so I use Scratch to make the game. I'll show you real quick. Can you see it?
Oh, so this is your program.
Yeah. So
Good.
I made these objects and different coding. And so basically this is how we can move up and down.
Okay. Very nice.
And we can switch it. Oh wait, I forgot to unhide Einstein. Okay. Give me a second. The Wi-Fi is quite slow.
You can.
Okay, yeah.
Okay.
And so when the timer expires, you have to click restart. So let me restart. Yeah. This like a bug as well.
So what is this death ray?
It's basically light, and then we transform it into a death ray. And the goal is just to hit Einstein. I guess the Wi-Fi is not working with us.
You can use this room's Wi-Fi. It's password is there. Astro minus ADP.
Oh,
But what's the wavelength? I mean, the refraction angle depends on the wavelength, right?
yeah.
The refraction angle.
You mean the reflection angle
This
related
angle.
to wavelength?
Depends, no?
I guess I'll come back to that and
Okay. Okay, good. So Cody, did you do all the programming?
kind of, yeah.
Did other people help?
No, not really.
Did you help?
Like technique.
Okay, good job,
But, like,
Cody.
we discussed like the
We
whole
discussed.
like idea.
But the programming is by
Yeah.
Cody.
Yeah.
Okay, you guys are lucky you have the Cody in your team. Okay, good. So let's go to Serena.
So I'm Serena, I'm going to introduce the interference. So, in physics,
Interference, did you say?
Yeah.
Okay.
so interference is a phenomenon in which two or more coherent waves are combined by adding their intensity and displaying them with due consideration for their phase and difference. So, as we know, light is a wave, so of course there is interference. So, let's consider the two waves here with the same frequency travels in the same direction. And if we add these two waves together, so it's pretty much create a bigger waves. So this is called like constructive interference. But what happens if we add these two waves together? Like you can see it's up here and it's down here. It's like they cancel out each other. So it's called destructive interference when we add in two waves. So now we have the wave function. So here is the wave one. The A is the amplitude, and K is like the wave number. K is equal to 2 pi divided by lambda. And here's the angular frequency. So here we have another wave with another phase. This is called Wavy. And here is the phase difference between the waves in radians. So when we add these two waves, we have the result here. And cosine, when plus cosine is 2 cosine. Multiply cosine here. So why, when do we know it's constructive interference and when it's destructive interference? So we depend on the Wavy here. So when it is, the Wavy here is the even number, so it will cause the constructive interference. And if it's the odd number, it will cause the cosine here to be 0, and then it will cause the destructive interference. So we already know in the previous part that Cody and YouTube say that the concave mirror here is gonna reflect the light, and also convex mirror. And the two lens is gonna reflect the light. So why do we need to know about this? Why the light traveling through these optics give different results? So when the light from the air hit the objects, is another surface with a higher reflective index that will cause the light to reflect or refract. So, and why do we know to it when they reflect or refract? Because this will cause the phase change, and the phase change is very important to the interference, which we will know is constructive or destructive interference.
Right. Wait. So it's important, right? So, how does it work for the previous one, the lens?
Like we will play on the lens like this when the lens here is like convergent behavior, right? And it will reflect. So refract. So the waves when
Okay.
it's like the light when it here, it will diverge, but like the phase change and then causing the interference.
Yeah, that's important. Can you go back one more slide? Back. Yeah, here. Maybe you have another one. Go back. One more time. Maybe one more. Yeah, here. So,
This one?
yeah, here. So how do you make sure? How do you make sure the wave doesn't distract each other? In other words, in what kind of condition does the wave distract each other at the focal point?
When we combine all these
Yo,
reflected waves
yo.
and the total phase, the phase change will like they become like the phase change here is causing the cosine here is 0.
Yeah, so in that case of that lens, when does it happen? Can you add it to your homework, please? You explained a very important issue, but you didn't reach the conclusion and stop. You start talking about very interesting thing, and then, where's the conclusion? Where's the conclusion? And you stop. So, I suggest you add a conclusion to the report. But the topic was interesting. Yeah, very nice. And then Owen?
Yeah, hello. Good morning,
Yes.
Good morning, everyone. So today I'll be I'll be teaching you guys something about diffraction. Although we don't have a demonstration of the diffraction in our game, it's still an important topic to understand. So first of all, we know that light has two properties. It has a wave-like properties and particle-like properties. And then there's an interesting observation that we can observe when we shine a light through a narrow slit. So we know that light possesses both of these properties, because if light only behaves like a particle, then when going through a single narrow slit, it will only light up a bright light in the center and not much on the left. The same could be said for a double slit. Although in this picture it's a little unclear, but the middle part is a little bit darker than compared to the two. But in reality, what we see is something more like on the picture on the right. The single slit, the central part where it's shining brighter is obvious, but what we don't expect is these other lights that are happening over here. And the same can be said too for the double slits. They represent something like a wave. So we can see here that light is a wave that interacts with each other, and that's why there's some bright spots which we call maxima, and there's some dark spots we call minima. So what happens here is that because light has a wave-like property. When it reaches when it goes into a slit, it's sometimes spans outwards. So even from a small slit like this small part of light can expand forwards. We can see this property also happens when a light touches an edge. You can pay your attention to this right picture here. If you see carefully, sorry because the picture's kind of blurry. This property also, we can also observe the wave-like property of light, like when the light shines through the edge of an object. So over here you can see that the light here is very bright, and then you can see a slight dark tinge, which we call the minimum of the light. So why would this happen is because the Huygens pencil principle. Every light wave, the Huygens pencil principle states that every point on the wavefront can be considered as a source for another wavefront, which will then become another source for the victim, as shown. So we can see here that the initial wave of light, they can become the source for the next wave of light, and so on and so forth. That's why they expand towards. Can we go back one slide? One more slide. Yeah. So if light only behaves like a particle, then we would expect it only just to shine this part. But because of that behavior that we mentioned before, this light then expands way bigger than the slit size. Next. Okay. So how do we? So we can find consistency in the slits. We can find where the position of the dark slits is. So let's take this for example. Let's say there's a light wave coming from here, and then this slit size is called E. And then we want to find the first dark spot. So we call those. So let's say them P1. We first divide this slit into two evenly sized space, and then we project two rays of light. And then we see on which condition does this create a dark spot. So we can see that, so we know that the way that light interact with each other and they cancel out is because they are out of phase by exactly the lambda divided by 2 or their wavelength. If their wavelength are out of sync by half of their wavelength, then they will cancel out and then create nothing. So we know that if the difference here, if their path difference here is exactly half of their wavelength, then we know that they will cancel out and create a dark spot. So if we assume that the distance from the light and the screen is d, and then d is way bigger compared to the slit of the A, we can simplify some things and assume that these two lines are parallel. So we can do some simple maths and figure the path line difference is equal to this. Doing a little bit of simplification, we can find the first dark spot is exactly when this equation is true. Okay. We can find the second dark spot the same exact way. So this time we imagine dividing it into 4, and then also we figure out we point the light ray into some spot P2, and then we consider under what condition does this make a dark spot. If we also assume the same thing, when D is way bigger than A, we can assume that these 4 lines are parallel, and then we can know that the path difference between these 4 are also lambda over 2, which also gives us 2 lambda. And then from this we can generalize that to find any other dark fringe, we just have to add, multiply by 1, 2, 3, or whatever number of dark fringe we want to find. Thank you.
Okay, so Owen, that's good. Homework. How does the light intensity changes as the M changes 1, 2, 3?
Excuse me?
How the light intensity changes as M goes 1, 2, 3, 4?
Oh, it becomes lower because,
Yeah, how much lower?
can I write that on my report?
Homework, yes.
Yeah.
Thank you. What's good report, Owen?
Thank you.
It was actually reported the last time this double slit experiment, but your explanation was better. So,
Thank
so
you.
that's good.
Thank you.
Okay, Vicky.
NVT, and I'm going to talk about the relativity.
Okay.
So first, the background. In physics, the principle of relativity is the requirement that the equations describing the laws of physics have the same form in all admissible frame of reference. However, by solving the Maxwell's equation, we can find that the speed of light is fixed, which is contradicts to the Newtonian mechanics. So, Albert Einstein proposed the postulate of relativity. And the first one is the laws of physics are the same for observers in all inertial reference frames. And the second one is the speed of light is the same in all directions and in all inertial reference frame. In classical physics, we use Galilean transformations to describe the relative motion between two objects. And it correlates that the space and time are absolute, that no matter which frame of reference it is related to. But it is contradict to our the second one that's page. So we tend to apply the Lorentz transformation. It says that the space and time are not independent for each other. There's no absolute space and time, which means our coordinate system should be expanding from 3 systems x, y, z to 4 dimension at the plus the time. The time is no longer exists independently of space. So under these conditions, we have some discoveries. Since in the inertial frame of reference, we always think ourselves are stationary. So if we let the speed equals 0 in Lorentz transformation and replace t by delta t, then we can have the equation. It means that if we both hold a clock and you working with a constant speed, then I will found that your clock will slower than my clock. And in other words, this means that the concept of simultaneous is relative, not absolute. And similarly, after some calculations, we can have these equations. It means that the observer sees a decreasing in length to an object with a zero relative velocities. So, and after that, I'm going to talk about the mass. In relativity, the environment mass is an environment quantity which is the same of all observers in all reference frames, while the relativistic mass is depend on the velocity of observers, and this is the relation between these two mass. It means that no object with non-zero mass can reach the speed of light because this cannot be negative in the root. So by that equation, we can modify the Newtonian mechanics to make it wider. So after this step, we can at least is the generalized of Newtonian mechanics. So, and about the energy, we define the rest energy by E0 equals mc squared. And we define the total energy by E equals E0 plus kinetic energy. So,
Time is up. Okay.
and by this relation, we can generalize that equations.
And the equation, the difference between this and E equals mc squared is that that one is for the rest state, and this one is you can apply when you are moving, you have speed and you apply this, and your speed, and you are your statistic, and you can apply the E equals mc squared. That's my.
Okay, so Vicky, your homework, okay, the 50% of speed of light spaceship, and Chase is 70% of the speed of light spaceship. What's the relative speed? Can you show the calculation? The two spaceship, okay, flying, 50% speed of light, 70% speed of light. What's the relative speed difference between them? Okay.
So,
Okay, you have 1 minute to show the game.
yeah, so Einstein is back, and then we can, as you can see, you can switch the bands, and then, okay, I'm very bad at this game. Okay, yeah, so when the ray hits Einstein, the timer resets, and we get a fresh 10 seconds to continue play the game. Yeah, so this is, and the goal of the game is try to reach as a high score as you can. Yeah. And this is it. And you can move it up or left, right, move the ways to change the direction of light. Yeah.
Mhm.
This
So
is
just
it.
one of them hit Einstein, then it's okay.
Yeah, just one of them.
Okay.
And so the two rays are like representation of like an image. Like,
Okay. Good. Claudia, as I said, the refraction depends on the wavelength. So how did you
Yeah.
calculate the refraction? So you must assume some wavelengths here, right?
yeah, so I just like assume like it's like I didn't really like specific wavelength. I just assumed like in general.
Okay.
Yeah, so I didn't calculate the exact wavelength.
But you consider where you hit the lens, right?
Yeah.
Okay. Good. Very nice. Very nice.
Yeah.
Okay. I like this game. So can you share the game?
Yeah.
So so that I can play later?
Through your email or in the report.
Yeah, me and report will be better. Yeah, me and TA. So
Yeah, it's also like shared docs. So I think everyone can.
okay,
Yeah.
good. That's good. Okay, very nice. Thank you very much.
Thank you.
Group 19. Okay.
It's okay.
Then group 15. Let's go. Please write down your names, and then your 35 minutes gonna start now. So please make sure to finish within the time. Oh, you made this?
Yes.
Ooh, very nice.
Thank you.
So these are interesting.
These are games. I will explain the presentation.
Okay, very nice. You're Anna, right?
Yes.
Okay. Jody is where? Where's Jody? Jody is there. Okay. Did you share the screen online? Can you can you log in?
So I joined the Google Meets, but no one answered. But why?
No, it's automatic. Try again. It's automatic. Okay. So Sorry, can you guys write down your student number? Because otherwise, two names cannot connect it without some other parameter, right? Alvin, who's Alvin? Okay, Alvin's here. What is this? Who's Nishije?
That's me.
Okay, what's your English name?
Jay.
Jay, okay. Lin Mingkang. Lin Mingkang, what's your English name? Mingkang, okay. How many people are you? 5? Okay. So try to finish 7 minutes each. Yeah, so that you can finish. Okay, let's go.
Hello, everyone. We are group 15, and today we are happy to present to you the game that we created.
Okay.
And it's called Wormholes and Rockets. We made this game in hopes that we will be able to educate players in very complex topics. from
Sorry, can you mute the microphone?
Laptop microphone.
And then also speaker.
I already muted.
Then it should be fine. Let's go.
I'm in the right corner. That one. Your network house.
No, I think it's fine. As long as your volume is 0.
Yes, it's
Speaker volume. It's not 0. That's why echoing. Okay.
Okay.
Now it's okay. Yes, it's okay. Let's go.
So we created this game together in hopes to be able to educate people on very complex topics of astrophysics, such as we want them to understand the big questions that are what exactly are stars, how are stars made, and what is the life cycle of a star.
Interesting.
Next week. And we're hoping to be able to achieve this with this game board that we created, inspired in the classic game called Snakes and Ladders. We just did a variation, including concepts related to space, and we incorporated some play cards in order to make sure that players are understanding the physics projects presented in the game. Here are an example of the game cards that will be asked in the games. As you can see, these are topics related to how stars are made, the processes that goes within the stars, and also related to star death.
So the rule of the game is basically
You're Jody. Okay.
the rule of the game is basically snake and ladders, but the difference is that when you land on the wormhole or the rocket, we give you a challenge, the game card, and then if you land on the rocket and you answer correctly, you can go up.
Okay.
But if you don't answer correctly, you just stay there. And if you land on a wormhole, if you answer correctly, you don't go down. But if you answer incorrectly or don't answer, you go down.
Okay. Oh, this is good. Good.
Yeah.
So you need a physics. You need to answer physics questions, right?
Yeah.
That's good.
And the questions in the cards will be explained on the presentation.
Very nice. I like this game.
I just wanted to explain the game pieces. We will be playing as little clouds, and the cloud that be able to reach the square number 100 is the cloud that will be able to become a star.
Okay. So if you reach 100, you win.
Yes, you become
Okay.
a star.
Okay. You can be a star.
Yeah.
Like that when your dad dies and you become a star.
Yes, you will go to space.
Okay.
Next, this these are the topics that are covered in the game. And so my teammate Alvin will gonna start with what is a star?
Okay, good, very nice.
So, morning, Professor. I'm Alvin, and I'm going to explain some physics. And the first one is what is star? A star is a ball of gas, and it is held by gravity. And at the center of the star, energy is released through nuclear fusion, which exerts output pressure, which is the green sign here. And when output pressure is balanced the inward pressure, which is gravity, we will call it its hydrostatic equilibrium.
Right.
And in the process of energy is released in form of neutrinos and photons. So neutrinos don't really interact with anything, and they just give the star. So we can say that it is basically a source of energy loss. And the inner energy in the photons is dumped into the star, and this is why hits the star. And it will also cause the outward pressure. So for fusion to take place, you need a temperature of about 10 to the 7 Kelvin C. And this image is fusion.
Okay.
So how is the star formation? If we have a gas cloud here and it is self-gravitation gas cloud, when it starts to collapse, it will heat up until the nuclear fusion. And so we're going to talk about when will it collapse. So if there is gas cloud here and its length is L here. So if there are some disturbance here, the particles here will bump into some other particles, and these particles will bump into some other particles. So this disturbance will propagate to the other side of the cloud. The speed of the propagation, we'll call it, it is speed of sound, because sound is some particles bump into some other particles. So we will talk it. So the time for disturbance from here to here, we will call it Ts, T sub s, and it's equals to the length divided by the sound, the speed of sound, which is Cs. And the star will be unstable if Ts is bigger than TFF. TFF is falling time, free falling time, because it's gravity here, and so particle will falling from the edge to the center of the star. So we want to know what is the free falling time, so we can use the equation of conservation of energy. So we can write this equation here. This is kinetic energy, and we convert the velocity to this, and if we minus to the gravitational potential energy, these two will roughly be zero because it's this big body. So if we take the potential energy to the other side and we cancel the mass here, we can get this. And by root square the both sides, we'll get this one. And we can integrate by 0 to half of the length, because we are considering the edge to the center, so it's all just half of the length. And this side will integrate the free falling time. And the minus sign, negative sign here is because it's informing but not outward. So by calculation, we can get free falling time is roughly equals to this one. And the cube of length is the volume of the gas cloud. This one divided by the mass, we'll get the density of the gas cloud.
Right.
So we can roughly get the answer is this. And I will cancel all the numerical vectors because it's just
Just a
roughly calculation.
constant, yeah.
So by this, we can get this equation, and if we take this CS to the right side, we can get this. And this is called Jan state. What is Jan state? It's if a self-gravitation cloud becomes too extended, and it will go unstable, which means if this one is too big, the star cloud will be unstable. But it doesn't mean if the length is too big, it will 100% collapse. It's just a probability, but not for sure. So I'm going to talk about what is speed of sound. We can get the equation from here. The square root of speed of sound is partial derivative pressure with respect to density at a constant entropy. And constant entropy means no heat flow. And by ideal Maxwell and Boltzmann gas equation, we can get these two ones. This one is by PV equals to NKT, and I put the V to the right side, and we can get this one. And another equation is this one. And in a diabatic process, which is constant entropy, we can get this one, this equation here. The pressure will be equals to a constant K times density raised to another constant gamma here. And gamma for monatomic gas is 5/3. So by calculation of these three equations, we can get the start of speed is equals to the average particle speed, or we can say this root mean square velocity. So this is my part.
Okay, very good, Alvin. Very nice.
So I'm going to talk about
Can you state your name at the beginning?
Judy.
Oh, sorry, it was there. Okay.
I'm going to talk about the minimum mass of a star, theoretically possible minimum mass of a star.
Okay.
So to derive this, we have to use the Ferrier theorem. It says a system average kinetic energy is related to its average potential energy. And in the context of a star, the average kinetic energy is its temperature, because its temperature is basically the total of the vibration of particles in the stars. And then the potential energy is the mass, using the Newton's law of gravitation. So for a system with average kinetic energy, Ke bound by a potential force F equals minus gradient U, and U is constant R to the power of N, where K is the constant, R is the interparticle distance, and N is the power of the potential energy function. So Ke becomes N over 2 times the average potential energy, where this is the definition of the Ferrier theorem. And it becomes N over 2 because the Ferrier theorem also states that if a force between any two particles is proportional to the distance, it will becomes n/2. So this is a fact that we can take for granted, that the minimum temperature for a fusion to occur has to be greater than 10 to the power of 7 Kelvin.
Mhm.
Using this fact, we can start the calculation where delta X, which is the Heisenberg uncertainty principle, says that we cannot know for sure the position of a particle is inversely proportional to the momentum of a particle. And because we can substitute the kinetic energy, which is half times mv squared, to the temperature, this becomes this. And we get the equation of kinetic energy in terms of temperature. And this is the density. I think we can also take for granted this equation, and then we can substitute the delta x we get from earlier, and that becomes that equation, where this equation is an expression of density in terms of temperature. And mu is the molecular weight of a particle, and that this denominator is basically the volume of a sphere, where 4 pi over 3 times radius cubed, where radius is delta x over 2. And using the Freire theorem to relate to the potential energy to kinetic energy, we can get that equation.
Well, what did you assume for n?
Which one?
N, the power. What did you do?
1.
Why?
Because the source I used said that the Freire theorem is, we don't know if it holds up. It's very theoretical. Right?
Okay.
And so if we want to really derive it, we have to add a lot, like number in front, like half or something like that. So we use 1 instead to not overcomplicate things.
Okay.
Yeah. So this becomes that equation.
Okay.
And so this is the kinetic energy. We can substitute to the temperature. And this is basically volume. This is the volume of a sphere, and that's the m mass over density is volume. And so we can get this equation where it is a equation of temperature in terms of density and mass, just by substitution.
Okay.
And then substituting that to there, the expression becomes this. And now we can plug the numbers, where the mu of a star is 0.6, because we just assume that since stars are mostly hydrogen, we assume that the mu is 0.6. So T becomes that. Let me remember.
Okay.
And so we can set up the inequality where the previous equation has to be bigger than the minimum for fusion. And solving for M, we get the mass, which is 0.5 solar mass. And this is, note that small or medium stars are supported by gas pressure and massive stars are supported by radiation pressure.
Very nice. Okay, Jody, very nice. I like that. Good job. Yep. Okay, then Anna.
I'm Anna, and I'm going to talk about luminosity of stars. And this follows up with the previous conversation, as this can make a notion of how we can understand how big stars can really get, which is much more difficult to calculate. But first, we want to say that we know that stars are supported by a combination of radiation pressure, which is basically photons, and gas pressure. And as a general rule, we know that the more massive a star is, the more dominated by radiation pressure. Most stars, however, are dominated by gas pressure. Most famously, the sun is 99.9% gas pressure dominated. And the sun is actually much like a medium-sized star, not really a giant star. So when we talk about the luminosity of a star, which is completely dominated by radiation, this is what we denote as Eddington luminosity. In this case, if we look at the diagram, we can see that as gravity is trying to compress the star, the pressure that is pushing outwards and balancing it is just basically photons. And if we pay more attention to this incident, when a photon interacts with an electron, we see that it will scatter off, but it will also create some momentum in the electron, and the proton will follow it because they have an electric attraction. But one might ask this question: why does the photon interact with the electron, which is much, much, much smaller, not the proton, which is very big? Well, this is because of the scattering cross-section, because this interaction is actually proportional to 1 over the mass squared. And we know that an electron is about 1,000 times lighter than a proton. So that would mean that the scattering cross-section for the electron is about 1,000,000 times greater than that of the proton. So while it is true that some photons do scatter off protons, we can safely ignore this interaction, as it would be like 1 in a million correction. The Eddington luminosity gets its name from the British astrophysicist and philosopher Sir Arthur Eddington. Continue, please. So how do we calculate such luminosity? First, we say that the force on a single nucleus will be the radiation pressure times the cross-section. And this has to balance out the force of gravity. So we can write this as the force of light, as the force of luminosity divided by the speed of light divided. We can write this as the this equation is just like force and the probability that the force will interact with the electron, which is the scattering, the Thomson cross section. So how does this equation come to be? If you look at this area, this is luminosity divided by the speed of light. So if we divide energy per second by the speed of light, we get momentum per second, and that's just force. Then the probability that one of those photons will hit an electron is going to be the electron cross-section, which is the Thomson cross-section that I mentioned just now, the electron cross-section, and which is divided by the surface area of the star. Just a point, the Thomson cross-section is just a number that I'm not going to show how to calculate, but it's just 6.65 times 10 to the minus 29 meters squared. And now we can equate this to the gravitational force on a nucleus with an atomic number A and a charge C. And we include A and C
Mhm.
because this may be a little bit confusing one, but here, because photons are scattering off electrons, but we're putting into the gravitational force on the nucleus. This is all because the mass of a star is contained in a nucleus, as one proton is 1,000 times heavier than an electron. So electrons don't really contribute much to the mass of the star. And also, I mentioned that the nucleus has a charge C. This is important since the star is electrically neutral. There are so many protons as there are electrons. So C will tell you the number of electrons per nucleus. And if so, radiation force is being transferred to a nucleus via an electron. It matters how many electrons there are per nucleus, so we have to multiply by a factor of C. So now here we can cancel the R's, and we solve for luminosity. And we incorporate this Y, which is just C over A, which for most stars is 1. And if a star is completely made up of hydrogen, it's just going to be 1. So we make this assumption.
Mhm.
And so we get that the Eddington luminosity is about 10 to the 31 watts per star and unit solar masses. And in order to grasp this, we can compare it to the solar luminosity, which is 4 times 10 to the 26 watts. So we can see that the sun is not really big. In fact, the stars can go as big in base of their luminosity, maybe like even 100,000 times or bigger. Next, please. Now, I want to talk a little bit about gas-dominated stars. This is a little bit complicated topic because we need to talk about the photons and how the particles move in a fluid. That's the diffusion equation right there. In order to be able to derive this equation, one must require a very extensive knowledge of thermodynamics. But if we look closely at the components of this equation, we can understand a little bit the interesting information that it can provide about stars and their energy and how it's related to density and temperature. So here, we have the luminosity, which is just a derivative of time of energy. And that's going to be proportional to the surface area times the radial component of the radiant of the energy density. So U over there is just photon energy density, which is proportional to temperature to the 4 there in the corner. And what does this tell us? This is basically saying that the change in energy density, it moves away from, as you move from the center of the stars outwards. It's like radial direction. So it's considering how energy in the star, how energy is distributed within the star and how it focuses as you move outwards. In simple terms, this is telling us that how the velocity of the star is influenced by the size, the energy within the stars, and the temperature. And now this constant d, this is called a diffusion coefficient. And it turns out it's approximately a third times the speed of light times the photon mean free path. And as I said before, the photon mean free path is just a way to say how far the photon can travel without interacting with anything. So from this equation, once we plug everything in at the surface area, this is the mean free path, can be rewritten as this. And the quantity here is the derivative of energy density times the 4. And for this term right here, we're gonna make this assumption, which is not very correct, but we can make it in this case because we're just considering the external luminosity. As you can see, this is not true when v equals 0, but as I said, since we're ultimately looking at the external luminosity, it's not a bad approximation. So now we're going to use the Birol theorem that
What is B?
Oh, B is just some constant.
Okay.
We can, later on, we'll group all of the constants together to some constant C.
Mhm.
Jumping ahead over here, once we use the Birol theorem, we can rewrite the luminosity. And this term in parentheses can come from the Birol theorem. And if we group the variables together, we have this term. And if we see this 3m and the surface area. This is pretty much just density divided by density, so equals to 1. So then we can conclude that the approximation that the luminosity of gas-dominated stars is basically 1 solar luminosity times the solar mass to the cube. Finally, let's take a look at real stars. As real stars are a combination of these two models. Since they both have gas pressure and radiation pressure. The way it is typically done is that the luminosity model is modeled as a constant times the mass raised to some exponent, and that constant will vary depending on which exponent you pick. And then what is done is that the model is fit with empirical evidence for various mass ranges. The most commonly used model is that luminosity equals 1.4 solar luminosities times the mass units of solar masses raised to the 1.5 power. As you can see, the model only holds for a mass range between 2 solar masses to 55 solar masses, and as you can see, it doesn't hold for the sun. Because if we plug in the sun, it would be off by a factor of 1.4.
Right.
But this is the most commonly used model because it fits a quite large range of stars' masses, and most stars that we know about will fall within this range. Thank you.
Very nice, Anna.
I'm Sijin, and my part is proton chain. Before that, we know that stars are powered by nuclear fusion in their core. Let's have a quick review about nuclear fusion. Nuclear fusion is a process which 2 light atomic nucleus combine to form a single heavier one while releasing massive amount of energy. Fusion reactions takes place in a state of matter called plasma, which is a hot charged gas made of positive ions and free-moving electrons with unique properties distinct from solid, liquids, and gases. And here is the graph for the nuclear fusion. You can see that the 2 light nuclei combines to 1 heavier and release the heavier one and energy. And the next is proton-proton chain. We will see that in the proton-proton chain graph, hydrogen is fusing into helium by fusion reaction. It's a multi-step process involving protons, which is the positively charged particles in hydrogen nuclei. The first step is the 2 protons collide and fusing to form a deuterium nucleus, emit a positron and a neutrino, which is shown that here. The 2 protons and the result. And secondly, the deuterium nucleus fused with another proton. This reaction creates a helium-3 nucleus and releases a gamma-ray proton. And finally, which is the most important step, is the 2 helium-3 nuclei collide. This collision results in the formation of a stable helium-4 nucleus and release 2 additional protons. The helium-4 nucleus is a key product of this chain, showing how stars convert hydrogen into helium-4 over time. We can know that the composition of stars is about 75% of hydrogen and 25% of helium, and most of it is helium-3. This is the key step because it will emit 2 hydrogen atoms and start another chain reaction. And here comes the electrostatic repulsion. The 2 protons require about a really high speed, about 10 to the power of 7 meters per second, to overcome the electrostatic force since it's 2 positive ions. When it becomes close enough, about 1 nuclear radius, the strong nuclear force will take part to make the chain reaction happen. Strong nuclear force only shown when the distance is close enough, and it becomes weak when it is far away. Yeah, that's all.
Okay.
So, and I wanted to talking about the triple alpha process. First, we know the hydrogen of the star core fused to helium and it's turned to the helium core and outer layer still hydrogen because we are not hot enough. When no more hydrogen diffused, the star will start to contrast and become hotter until the helium fission is occur. So the outer layer will push up and become created as a stage red giant. So now I will talk about the triple alpha process. Triple alpha process is a set of the nuclear fusion reaction by which 3 helium-4 nuclear such as the alpha particle are transformed into the carbon-12. An important nuclear reaction that occurs in the core of the star more massive than the sun. So we can see here we have 2 helium like the alpha particle, and we collide together become a barium 8, and later we have collect another helium particle, alpha particle to become a 12 carbon. So the triple alpha process has a 3 steps. The step 1 is the first fusion, just like I say, like the 2 helium-4 nuclear fuse to form barium 8 nuclear. The step 2 is the resonance step. The
We're too loud.
yeah, the barium 8 nuclear is highly unstable and quickly decay into the 2 helium-4 nuclear before it can capture another alpha particle. So during the step 2, the barium 8, during the step, they have almost the energy of the excited state of the 12 carbon as well as the Euler state, and that can increase the probability that incoming the alpha particle combine with the barium to form the 12 carbon. So we come to the third step for the second fusion. Another helium-4 nuclear fused with the barium 8 nuclear and result to form a carbon 12 nuclear. So a critical role in the nuclear synthesis of the heavier element in the core of star. For the star with mass greater than Sun, when the core temperature and the pressure are higher, helium fusion by triple alpha process become a dominant pathway for the production of the carbon. So out here is the nuclear fusion stage. So the stellar nuclear synthesis is the nuclear fusion state refer to the various phase of nuclear reaction that occur in the core of a star. These stages are characteristic by the fusion of the lighter element into the heavy one. So here we have a few layers for the hydrogen, helium, carbon, oxygen, silicon, and iron. So this layer is mean that the star is more heavy or lighter. Next. So here is talking about the star depth. Talking about star depth, we can divide to 2 sections. For the first is the low medium mass star, and another is the high mass star. For the low medium star, something like the solar mass less than 10, like something like our sun. There's 2 steps for the depth. For the first step is the red giant phase, like the planet become vibrate, and the second step is the helium fusion and the planetary nebula formation, and the third is the white dwarf formation, become a white dwarf planet, white dwarf. And then for the high mass star, when he collapse with a collision, it becomes a supernova, and the supernova will become to a neutron star or the black hole formation. Next. So here has the 4 picture. For the first one is the white dwarf and supernova, a neutron star, and the black hole. And this 4 is about the star depth. And once the star gets to an iron core, it can no longer generate energy through the fusion and get a core collapse to the supernova. And it will remain a neutron star and a black hole depend on how massive the star. Depend their solar mass. If the solar mass is less than 10 and the fusion stops at the layer between the carbon and or the silicon or oxygen, it will shape it outer layer to the planetary nebula to form a remain as a white dwarf, which is possible to explode to a type 1a supernova when it reaches a Chandrasekhar limit. And next. So here is the stellar life cycle. You can see when the star becomes a red giant, it will collapse and become two remand for the planetary nebula, and it will become a white dwarf and a dust. And for the massive star, it become a red supergiant and become a supernova and divide to the black hole, neutron star, and the dust. And the dust will all combine together and make the cycle run again. Here's my topic.
Very nice. Excellent. Okay, so you guys finished them all? Okay. You guys did an excellent job. Can we try this, or are you going to? We don't have much time actually, but then yes.
Would you like
we-
to be asked the question?
Yeah, sure. Why not? Do you want to try that too? Yeah. Who wants to try? If you want to try, come here. Come here.
We're just gonna ask the question, but see if
So,
Okay, Professor, you go first. Your question is, when are black holes created?
when black holes are created, when the I'll explain, right? When the massive star dies, right?
Yes, when a massive star is able to fuse, is not able to fuse iron.
Okay. So,
So if you were, let's say you landed here, you got the question right.
Yes.
So you go to square 38. You're closer to becoming a star.
why I jumped 4 to 38?
Rockets.
Let's say
Oh,
if you roll the dice and you land on 4,
okay.
you answer right the question, so you
Okay.
can go up. If you
Okay.
would answer incorrectly, you would just stay here.
I see.
So
I
you
see.
open the door, you can go up. I'll ask you a question.
Oh, do I roll the dice or?
Oh, if you want.
wait.
But it's not,
Oh,
maybe
okay.
you won't.
No, it's okay.
I'll just ask you.
So what happens if you come to 7? You have a chance to
No, no,
jump to here.
no. This is like
If you-
only if you land in 26. If you answer the question right, you won't go down. But
Oh,
if
but
you
if-
answer incorrectly, you will go
Oh,
down.
dangerous. Okay. Okay.
So this is your question. You have to fill in the blanks. Strong nuclear force is blank at short range, but blank at long range.
Stronger and weaker.
Yes, as you can see, strong nuclear force.
Oh, okay.
So you also will go up.
Oh.
TA, your question is, why are most stars unable to undergo nuclear fission beyond iron?
Because beyond iron, because the fusion potential like over the iron is too large, so iron is the most stable heavy material that fusion can make.
Well, we wrote this because they're not massive enough. I think this is much more easy answer than what you said. But
You
basically,
mean stars are not massive enough?
to be able to fuse iron, in order to be able to complete to iron fusion, you need very big mass. That's why most medium stars cannot be able to fuse beyond carbon.
Is that true? Is that true? If the stars are massive, they can fuse iron?
Most stars won't fuse iron. They won't go that down.
Right.
Just very big stars will be able to do so according to our research.
Okay.
Is it correct, Professor?
I thought your answer was.
No. I think I misunderstanding that.
Maybe, yeah.
I'm thinking that she asking why we can further nuclear.
Yeah.
Further.
Right.
I think
I'm answering that, but I think that's not she's
Perhaps.
asking.
our question was worded not very clearly.
It's okay. It's okay. We can check it later. Yeah.
Would you like another question?
Yeah. Why not? So you created this too?
Yes, we
Very
just
nice.
and
Oh.
dices, and this is you're a little cloud, and you
You bought this, right? At Sogo.
Sogo.
Oh, Amazon.
This one it was created on online, and we printed, and then we
Oh, you bought it online, right?
no, it just on Canva,
Okay.
and then
Good.
pasted.
I'm just saying it's
Oh.
the quality of the game of the game that's
Oh.
sold online, something like that. So, very nice. What is that to start?
Oh, once you win, this is your prize.
Oh, thank you. Thank you.
You answered correctly. I'll give you a
Okay.
star too.
Oh, okay, okay. Oh, it's okay, it's okay. Very nice, very nice. You guys created a question together? Or Anna created them all?
The question or the cards.
Question. Yeah, cards.
I create half the cards.
Half of them? Can you see?
Yes.
Oh,
How many cards is here?
25.
very nice. How many did you create? You create half? You create half?
Minkan and
Okay.
Alvin created the cards.
Oh, that's why there are a lot of questions about nuclear fusion.
Yes. It's based on everyone's lecture and everyone helped to assemble and cut and
Oh,
the content.
these are very nice. Yeah, these are kind of game that I was hoping that you guys make, because it's educational, right? Like by playing, we can learn, right?
Yes.
Oh, very nice. Yeah, I hope we have the time to play it more thoroughly, maybe. But then I guess we ran out of time today.
Do you want to keep it for yourself?
Can I?
Yes.
But don't you need it?
No.
No.
We have the soft copy.
We have
okay.
we have the online version.
Okay.
You can keep the physical version.
Okay. So can I keep and then maybe
Yeah,
play?
You
with,
can store
yeah.
here the
Okay.
pieces of you.
Oh, thank you. That'd be wonderful. Well, I want to check the questions, you
Yeah,
know,
of course you can.
one by one. Maybe I'll test my students. Test my TA.
And these are the game pieces, and I'll put more.
Very
stars.
nice. Oh, this is excellent.
I'll put more stars there, so you can.
Thank
keep
you,
the
thank you.
winners.
Okay, this is excellent. Yeah, this is the exact reason, you know, the purpose of this class. So, thank you very much.
Thank you, Professor.
Okay, thank you. This is very nice. Okay, thank you very much. I hope other groups can follow you guys how they do this.